Good. So let me summarize a bit of what we did before the break. We formally derived the master equation for Markov processes with discrete states. The Q matrix, or generator of the stochastic process, has the property that all entries are real. The out of diagonal entries are non-negative, and the diagonal entries are non-positive. The row sum needs to be 0 because probability is conserved, and we showed that this means that we must have some steady states. Question now was, what happens if we look at particular subspaces, those which are irreducible? That means all kind of transient states have been dying out, the absorbing states are away, you are in a space where every point can be reached from any point in a finite number of steps. That's what I mean by that. So, and for that, as I announced before the break, you can show that there is a unique solution for the steady state. And for that, we need the Perron-Frobenius theorem. And let me just read it to you. So it formulates a theorem for a matrix M. The matrix M has only non-negative entries. That's not what we have, but we can make it non-negative, as you will see. And if that's the case, if the entries are non-negative, then there will be a dominant eigenvalue out of the many complex eigenvalues that you can have. And this dominant eigenvalue is such that all other eigenvalues are within a circle. And the circle radius is given by the dominant eigenvalue. Okay, so when I draw this here on the board for this theorem, you have here the spectrum of a matrix M with the entries M and M being non-negative. And then you know that there must be a circle. And on that circle, there must be an eigenvalue which is real. It's called the Perron root. And all the other eigenvalues, they must be within that circle. They can also be on the circle. Okay? So the statement is that the absolute value is less or equal than lambda. Okay, so let me draw one here. So there could be also eigenvalues that have the same magnitude. But if this matrix is indecomposable, and we had this, right? This means that there's no invariant subspaces, or in terms of our graphs, you can reach any point from anywhere on the graph in a finite number of steps. Okay, so if this M has no invariant subspaces, then you don't have the equal sign. So for M being indecomposable, you have a strict inequality, and that means this cannot happen. Okay, there's a unique Perron root on that unit circle, and no others are on that unit circle. Not complex, not real, none of them is on there. Okay, that's the statement. And now let me go and see how we can translate this to our case. So what do we have? We have a matrix Q, but now let's define from the matrix Q a matrix M. So I'll take our Q matrix, and it has negative entries where? On diagonal. So let's take the largest negative, so the smallest one, the largest negative one, and subtract that. So I'll add this, so meaning plus alpha delta nm, where the alpha is the maximum over Rn of the diagonal entries absolute value. Okay? And when I add this maximum to my Q matrix, then I'm guaranteed that the object I will get out is a non-negative matrix because I have added that part that makes it negative. Okay? So that means when we take our Perron-Frobenius theorem, that we conclude from that there must be an eigenvalue lambda, a Perron root that exists, and I can rewrite this. So I can write this as sum over m q n m p m lambda equals lambda minus alpha p n lambda. Okay? So this here is the eigenvector to this matrix M. The lambda is the eigenvalue to this matrix M. And because of that construction, if I want to know the corresponding relation for Q, I just have to add or subtract this value of alpha here on the right-hand side. Okay? That's the conclusion we can make. Now, can we say something about this equation that we derived from the theorem, Perron-Frobenius theorem? We can, because we can now exploit the fact that the row sum here is 0. So here's n. Right? So let's sum over n. And as you sum over n, this will be 0. Because that's a row sum. And I will have a sum over n here. Okay? This sum over n here is a sum over n over all the probabilities, so that must be positive. So this here together with the sum must be positive. Okay? And that means lambda minus alpha has no choice, must be 0. So that means that we do have a stationary eigenstate using this Perron-Frobenius theorem that we just found by this very construction. And if our Q matrix is indecomposable, or in other words, it's a Q matrix where every state can be reached from every state in a finite number of steps, then this solution must be unique. Okay, so the consequence of this is that there must be a unique steady state for my Q matrix. Okay, so from that we conclude we have a unique steady state, and this is this P n lambda, and let's call this then Pn. And we know from the theorem that the entries of the eigenvector, the stationary state, is positive. That's part of the sentence. In that case, the eigenvectors can be chosen with positive entries only. Okay? So this is what you can conclude. So as soon as, and that's the simple answer, as soon as you have a subspace where you can reach anywhere. You have a unique solution, and every state is reached in a finite number of times, so it has a finite probability. None of the probabilities will be 0. Good, that's wonderful. But it's still a state that can have these fluxes, as we saw. So if I go back to this construction here, as you have it, so there are probability currents. I'm not sure I drew it right here, but there's something that can happen here in these states that has circular fluxes. Now let us look at a special case, but a very important case. So let's look at reversible processes. That means, in short, stochastic processes where if you run a movie forward and backward in time, and you infer the statistics of the stochastic process from the movies running forward in time and the movies running backward in time, you get the same statistics. Okay? You can't tell the difference between the movie running forward and running backward. That's the statement. More formally, if you do have a stochastic process, x of t, then you can look at a sequence of events from time 1 to time n. And in short, let me call this sequence here xt. If that sequence can be shifted by a certain amount of time, tau, backward or forward, then the process is called stationary. Okay? Because as you run the movie, you can take any window from that movie and you get the same statistics as you go through the movie. For an experiment, that typically means if you prepare an experiment in the initial state, there will be some transient happening early enough in the experiment, but after a while, the process is stationary. Any window in time that you have, you can use for sampling. Okay, so if x tau has the same statistics as xt plus tau, then we talk about a stationary process. Out of this subset, there is a more restricted set of processes. So if you have now xt having the same statistics as the process where you reverse in time and shift. So you look at the process running backward in time and shift it by some arbitrary amount tau. So if that's the case, then the process is called a reversible process. And of course, now if you have a reversible process, this must also be a stationary process, but a stationary process is not necessarily a reversible process. So let us draw now a trajectory for a stationary process, for a reversible process. So let's think of this axis here as our random variable, and this axis here as time. And let's look at different time points, t1, t2, up to tn. And let's say we do have a trajectory that assumes a value, some value here, some value there, another one here, and say another one there. This I call the forward path. And you can ask yourself, what's the statistics of such a forward path? What's the probability of having this particular sequence of events? That's my movie forward. And I can also look at the movie backward. And the movie backward, if I flip time to minus t, I can look forward in time again. So if I just match this now being the first point here at time minus tn. And I'm going back here to this point, and that point, and that point. That's minus t1, minus t2, minus t3, where I put tau to 0. So I'm really looking at a flipped process in time. This is now the backward path. Yeah, I'm saying that you get the same statistics when you look at forward and backward. Yeah?
Does it matter what tau is, or is this about
no.
stationarity?
This is part of reversibility. You formulate it such that reversibility implies stationarity.
Okay, so first it has to be stationary, and if then for every tau.
Yeah, but it doesn't make sense to talk about reversible if the process is not stationary.
Yes, that was my
Yeah,
question.
yeah,
Okay.
yeah. Okay. Then, so for those kind of reversible processes, we can make the statement which is called detailed balance. So it's the following statement. A stationary Markov process xt with a discrete irreducible, remember what this means, irreducible state space, is reversible if and only if you have numbers pi greater than 0. Those are the steady states, the equilibrium states, such that they are normalized. This is not a so important point. The important point is now that in that case you have the probability of being in J transitioning to K is the same as being in K and transitioning from K to J. Or in pictures, if you have two states, J and K, there's a certain probability of being in those states, which are Pj and Pk. And now the probability flux, so the probability times the transition rate from J to K, that probability flux is the same as the probability flux coming from the other side. And that's now special because it means that for all pairs, that for all of those, the net flux is 0. Across an interface that you put between the two states. So when you look back at the general graphs that we had, you cannot have circular currents because each pair of states needs to be balanced in detail. That's why it's called detailed balance. Okay? No flux is possible. How can we prove that? The proof is actually not that difficult. So let's start from the direction that it's reversible. Okay. Yeah?
Do you assume it to be stationary or also reversible?
Reversible includes stationary.
True, but you wrote just stationary, right? Or the SGAT, is it stationary? So it's a weaker statement.
What have it?
Reversible implies stationary, right?
Yeah.
But do we want this process now to be
Reversible. Because it's stationary anyway, then from my definition of reversible, reversible implies stationary.
So we should write reversible math processes.
Did I do this? Okay. Yeah, I don't need this. Okay.
Only stationary, we don't know.
Yeah. Yeah. It's kind of a silly statement then, right? So a Markov process is reversible. That's the assumption. That has an implication. And the implication implies that the process is reversible. Okay, so let's assume the Markov process is reversible. That implies detailed balance. And detailed balance implies it's reversible. That's what I mean. So let's assume it's reversible. Then if it's reversible, then, so that's assumed now. If it's reversible, it's also stationary by my definition. That means I do have a probability pi, which is the probability of my states having certain values, and that's something which is independent of time because it's a stationary state. So these PIs are numbers by the fact that the process is reversible. Now, I can do more with reversible than using that this implies stationarity. Reversible also means that I can flip the processes, so the forward and backward process have the same probability. That means if I look at a probability that at time t I have the value nt, and at time t plus tau I have the value of nk, then this is the same as if I look at the same probability but just exchange the two numbers that I have, the two values. So this is the same as the probability that I have nk at time t, and I have nj at the later time. Okay? Let's just switch the two values. Well, now, because that's the same, that's reversibility. This is also implication of reversibility. I can use that. I can write this in terms of a conditional probability by definition. So this is the probability of x t plus tau being nk, given that at time t it was nt times the probability of being in this state, n x t, this was j, being j, right? This is just translating this into that. And that is the same as the conditional probability that at the time t plus tau, I'm in state j, given that I was in state k at time t times pk. And now we divide this by d tau, which is the small time increment. Right, so write this as 1 over d tau. 1 over d tau. I take the limit of d tau going to 0. Then this left-hand side is transition rate. So it's w j to k, pj equals w k to j pk, and that's detailed balance. Okay? So reversibility implies detailed balance. Now what about the other way around? Let's assume that this is true, that I have a state like so, and detailed balance is valid. Well, I know this because of our theorem, the Perron-Frobenius theorem. There's a unique state, and the unique state has finite probability. So I need to show that given this, the process is reversible. So how would I do this? Well, look at the graph that you have there. Right, so this, and basically the backward is using the Gillespie algorithm in constructing an explicit probability for the path. So how would I start? I start out with the state 1 that has probability P1. And now I need to multiply with the probability of staying in that state 1 until time t2. So let's call the time here in between tau 1, etc. These then tau 2. So what is the survival probability staying in state 1? We had this. This is e to the minus alpha 1 t1, where the alphas, they are our exit rates. So it's the sum over k, and I'm going from I to k. Okay. So having those exit rates, I know that I stay in that state 1 with a survival probability that's exponentially distributed. Then at time t2, I have a transition from 1 to 2. Then I'm in the state 2, and I need to survive in that state 2 for a time tau 2. So this is e to the minus alpha 2 tau 2. And then I transition from the state 2 into the state 3, etc. Right? I can just repeat this. I concatenate what I would do in a Gillespie algorithm to calculate the probability of a path. And that goes then up to the point of going from the state n minus 1 to the state n, and then I have to remain there for the time tau n. That's the probability of the forward path. Okay, and now let me use detailed balance. Detailed balance you have here. So I can take this expression together with that one to write this as P2. So let me copy this one. And I can write this as 2 going to 1. Right? I'm going the other way. And I have to multiply by P2. But now the P2 has been shifted through and it's here. P2, W2 to 3, I can use detailed balance again, and I get, so let me copy e to the minus alpha 2 tau 2, get W from 3 to 2, and I have P3, and you see how this goes on. I can use detailed balance again and again and again for every one of these steps until I finally come to the point that I have then W, I'm going into n from n minus 1 e to the minus alpha n tau n, and finally the P, then the probability comes here at the last point. Well, then you just read it from the back, right? This is the probability that I start in n, remain there, transition back, etc., and I end up at my initial state. So this is nothing but the probability of the backward path. Right. So we have shown that. We have shown that reversibility for an irreducible system is equivalent to detailed balance. Okay. And let me now compare a bit what this means. So when we look at this graph here, in general, for a steady state, you have to have that the fluxes balance overall. So any flux into a given state has to balance the fluxes out of that given state. If that were not be the case, you would have probability changing over time. That's the overall balance that you must have for a steady state. For reversible systems, something special has to be the case, namely that each pair of states has to have a flux balance. Probability flux from that state into this state has to be the same as the probability flux from the other state back into the original state. And that implies, as I said, no fluxes are possible in such a detailed balanced state. All right, questions to that? Yeah.
Like in the case when Q is reducible, would it also imply some symmetry protection of the system?
See, the reducible cases always mean that when you go to the steady state, you lose probability from the transient states into those regions of state space where things are connected. Or it loses probability to absorbing states which kind of stay orphans and isolated. So in the long run, you may have that you have certain subspaces, right, that are irreducible on their own. The system could split from some initial state into certain subspaces that by themselves are irreducible. And that's the interesting case, right? Because all the other things, they're just transient. They're not a property of the final state. And then what I'm saying is I'm focusing myself on those parts of my probability of my state space where in the end I'm going to have everybody connected with everybody. And for those subspaces, I can phrase a condition on when detailed balance must hold, and that's when the process is reversible. Okay? So let us sum up. So we do have a Markov process. It obeys a master equation. this master equation does have steady states. The steady states are unique if the system is irreducible. And if in addition the process is reversible, then you have a detailed balance condition. That's as far as you can go with general statements about that. Okie doke. Then at the end of the lecture, I wanted to give you a few examples to illustrate that. And these examples are all one-step processes. And what I mean by that is I have a chain of states this may go on to infinity, to the right and to the left. Let's say I have here a state I call n minus 1, here state n, here state n plus 1. And by definition of these one-step processes, you have transition between the states in that chain. The lambda the rate lambda n that brings you from state n to n minus 1 is called a death process. And the transition that brings you from the state n to the state n plus 1 is a birth process. But now I guess you can easily write down the master equation for that. But let's look at certain properties of that. Let me add all the other arrows, right, because there will also be a rate like here, here, and back, here, and back. Same thing here. Okay. So what do you know now about this system, just by looking at the graph? In steady state, yeah?
Well, it's discrete and irreducible, so the steady state would fulfill the detailed balance condition.
It's irreducible, true.
We don't know time reversibility.
So that's the question now. So we know there's a steady state. And let's say there's a finite state space. Okay, so there's some n's here. So I can't get out to the left or to the right. And if you think back of what we did, all the calculations we did, all the theorems that we did were for finite state spaces. The matrices were not infinite dimensional, they were finite dimensional. Okay? So what else do we know here for a finite state space? Steady state. What has to be the case? In steady states, each probability that you see there has to be fixed in time. And so p at n minus 1, p at n plus 1, they all have to be constant. So that means there can be no net probability flux in or out, else they would be not constant. So that means in steady state, here the net current has to be 0 in steady state. But that's the detailed balance condition. So it means that stochastic networks with a linear structure like so, they must obey detailed balance because of the topology of the structure. You had a question?
Not a question.
Okay. Okay, so that means in a finite system, there must be detailed balance for those. And it's a particularity of these one-step processes. So now let's look at special cases. So let's say we have a linear birth-death process. So in that case, you would have mu n equals mu times n, and lambda n equals lambda times n. What's special about this process? Did I draw it right? I drew it wrong, right? Because if there's no individual, there is no birth process. Okay? So this system has an absorbing state right here. And that means in the long run, there will be no steady state. Or steady state is very trivial. It will be all dead in the population. Yeah?
Shouldn't the other, the probability of...
Oh, yeah, sorry. So this error, of course, exists. You can die, but you cannot give rise to a new individual. So no steady state or just a trivial steady state. Let's take another example. Let's take the 1D random walk. What is with a 1D random walk? Is it irreducible? It is. Good. So does it have a does it have a steady state?
Depends on the finiteness of the system.
Very good point. So if it's not finite, then we learned already from an analysis of the random walk that the random walk has a variance that goes to infinity as time progresses. So you don't have stationarity. It's not even a stationary process. It just vanishes, all the probability thins out as thin as possible. If it's finite, okay, so if I make a boundary, it's getting different. In this finite state space, you will have diffusion out, but then you have reflecting boundary conditions, and those reflecting boundary conditions make sure that you're going to have a steady state. And it's a very trivial steady state because the uniform distribution that you will get in the long run. So beware of systems that do have infinite state spaces. For those, strictly speaking, the theorems don't really apply for sure. Okay? Yeah?
Will it be a uniform distribution or like a stable structure?
Diffusion will not give you any kind of wave. Why not? We know this. because there's a unique steady state. It's a detailed balance state. There is no fluxes anymore that can happen. And if you have no fluxes, you can have no waves because there's no temporal evolution of the steady state anymore. The steady state is something that has a time-independent probability distribution function. Okay? So things like waves, traveling, standing, time-dependent, non-equilibrium steady states, you can only get if you have irreversible processes that don't obey detailed balance. Final question. What about a system that's on a ring? Can I still argue that this must have detailed balance? Why not?
You can have the circle flux.
Exactly, you can have a circle flux. Okay, so closed systems can again have a current. And it's about open system, finite systems where we can apply the theorems we just talked about. Great. Thank you for your attention. See you then next week. Question?
But this system could still have a detailed balance.
It could.
If it was time reversible, for example.
Yeah, it could. So if you say, now you have to require that the system has time reversibility, and then it cannot have a current, because a current you can distinguish from a backward and forward running movie. It would run right or left. Right? Yeah.
And also for the second part, basically, of the proof, when we said the steady state has a detailed balance condition, that we can from this imply that actually the entire process is reversible.
Mm-hmm.
Does this really work if we just look at the steady state? I mean, this computation where we move the detailed balance condition again and again, this was all in the steady state. What if we're not in the steady state and we make a mirror image of the path?
Okay.
Doesn't
So
do that, right?
for all these systems, you need homogeneity in time. That means if you have some initial transient, we have some specially prepared initial state that relaxes to stationarity first. There you can, of course, tell. Right? It's always about going into a window of time evolution where these initial transient states have died off, and you are in a time translational invariant stationary system. Okay?
So we are in a stationary state.
We are in a stationary state, and I define the reversibility to include the definition of stationarity. I could also, divide two things in terms of stationarity and the reversibility. Okay. But as said, it doesn't make sense to talk about reversible if the system is not stationary. Right? Yeah. Okay. Thanks again.